This is problem 8.59. It is on page 459. A 12-degree wedge is used to spread a split ring. The coefficient of static friction between the wedge and the ring is 30%. Knowing that a force P with a magnitude of 120 newtons was required to insert the wedge, determine the magnitude of the forces exerted on the ring by the wedge after insertion. Okay. All right, so there's some supporting ground just so that the ring doesn't move out of the way. And this is supposed to be a 90-degree angle despite my drawing. So there's the ring, except there's a split in the top, and they show a wedge with force P, which was, what'd they say, 120 newtons. And the wedge angle, which is important, is 12 degrees, so that would be this angle. And I haven't shown that the ring has some thickness. Let me add that in so you can see it. I guess I should put it on the inside, but anyway, there it is. Coefficient of friction, mu, is 30%. Okay.
Wait, how did you get that?
Just read the problem.
Oh.
All right, determine the magnitude of force exerted on the ring by the wedge after insertion. Okay. What kind of forces? Well, maybe we should analyze the initial condition where we've got 120 newtons of force. Of course, there's going to be some normal force on either side. And since it's symmetrical, I'm assuming that normal force would be the same. And since the relative motion, we stand on the ring and look at this wedge being inserted, it's going that way, so friction's acting in the opposite direction. Okay. I think we're supposed to neglect gravity because they didn't tell us the mass of anything. All right? So could we figure out the magnitude of the normal force in this condition? Because think about it. This ring is acting like a spring. The farther you open the spring, the more force it's going to apply, right? So there must be some normal force on it. So we just have a statics problem where we need to calculate the normal force and friction force. So let's sum forces in the vertical direction starting off negative 120 newtons. You know what? I prefer to use symbols, so let me use negative P. We set up a typical XY coordinate system. It would look like this. And then what? Well, we have to take components of the normal force. Notice that the normal force is at a slight angle up. Well, what would that angle be? Let me think about the wedge. Seems like it'd have to be 12 degrees, wouldn't it?
Yeah, 12 degrees.
Or would it be 6 degrees? I think it'd be 6 degrees, wouldn't it? Because if we look at the wedge and a vertical line, that's 90 degrees. It's 12 from here, so this is 6 degrees, right?
Yep.
And the normal force is going to be normal to this, so that means it's a 6-degree angle, not a 12-degree angle, right? So that means that for the normal force, this is going to be 6 degrees. We would need, in the vertical direction, plus n, well, there's going to be two of them, there's two sides, so plus 2n multiplied by sine of 6 degrees, right? Any questions about that? How about the friction force? Well, the friction force acts 6 degrees off of vertical. It's easier to see on the friction force than the normal force, that it's a 6-degree angle we're interested in. So it's the bulk of it that acts, so we're going to say plus 2 times the friction force times cosine of 6 degrees. Okay, any questions? See questioning looks. All right, so this should come out to 0. If we were to sum forces in the horizontal direction, that should be easy because, you know, where we have sine, essentially put cosine. We don't have P acting horizontally, so we'll just have, well, it won't be 2n, will it? It will be n times cosine of 6 degrees minus, on this side, it looks like we're going to have, well, everything's going to cancel out, isn't it? N multiplied by, still cosine of 6 degrees. The same thing's going to happen with the friction, because we're going to have plus, well, no, minus for this side, minus the friction multiplied by sine of 6 degrees, plus on this side, friction sine of 6 degrees. So this doesn't really help us at all, right? So this equation is not really all that useful, I'm afraid. Let's see. So we have one equation and two unknowns, the friction and the normal force. The sum of forces in the horizontal direction failed us. What should we do? That would be very useful. What's the relationship between friction and normal force? Do you remember? Friction force equals what coefficient?
30% of the normal force.
Friction, right. Why is it equal to that? Well, because it was slipping, right? It was slipping in. It was at the maximum. There was motion, so the friction was at its maximum. So this is the relationship between the friction force and the normal force. Now I think the normal force would probably be a little bit more interesting because where does the normal force come from? Does it come from P? Does it come from F? No, it comes from the ring. When the ring is open to different amounts, it's going to apply different amounts of normal force. It's just like a spring, right? So if the wedge remains at the position where we pushed it into, then the position of the spring is the same, and whatever the normal force was in this case will be the normal force in the next case when we remove force P. Okay? So I think getting at the normal force would be useful. So let's replace the friction force by mu m. And now we should be able to solve for the normal force. So we'll have P on one side equals 2 times sine of 6 degrees. Notice what I'm doing, I'm going to factor out n, plus 2 mu cosine 6 degrees times n. And so now the normal force n would be P divided by, I guess we could factor out a 2, times sine of 6 degrees plus mu cosine 6 degrees. Okay? So, plugging in the numbers, 120 newtons divided by 2 times sine of 6 degrees plus 30% of cosine of 6 degrees. And now I need calculator help because, of course, I haven't worked this out ahead of time. So, take your calculators, let's see what we get. First term, the sine of 6 degrees is going to be pretty doggone small. Not going to be much to that. Once you get a number, tell me what it is. What are the units of that number, by the way? They're just newtons. Let's see, what will it be about? Well, cosine of 6 degrees is about 1. 0.3 times 2 is about 0.6, neglecting the sine. So 0.6, so that's basically 120 divided by 6, which is what, 20? But it's an order of magnitude difference, about 200 or so, I think. If I'm thinking right. 0.6, yeah.
I'm getting about 148.93.
Seems a little small to me. I'm surprised it's that far away from 200. Anybody second that? Maybe right. Second it? Okay. I don't know what's wrong with my mental analysis, but there we go. So 148 newtons or so. Okay. Now that's going to be the same force when we remove force P from the situation. But now what's happening? Well, now notice that the wedge, the ring is trying to push the wedge out because the normal force is normal to the surface. There's a component that adds acting upward. So if we stand on the ring and look at the direction of impending motion of the wedge, it's up, therefore friction must be acting down. See that? So now we've gone to the time when there's no longer force P, and now friction is the only thing holding that wedge in. Think about it this way. If it was a perfectly lubricated surface, the wedge would just slip right out, wouldn't it? Okay? Okay. Well, that's a little bit different. How is it different? Well, let's see. Looks to me like the direction of the friction force is opposite, and this would just go to minus, wouldn't it? Because the normal force is still acting the same way. Oh, by the way, we don't have P anymore. The friction force, now will the friction force be equal to mu n or not? Maybe not. Mu helps us determine what is the maximum friction force that we could accomplish, right? May not need the maximum friction force. So could we figure out what friction force is necessary? Sure. Notice the normal force is still the same. This normal force is still 148 newtons, because that's determined by the ring and how far open the ring is. But the friction force is just going to be however much friction force is necessary in order to hold the wedge in position in the ring now. So let's go ahead and cancel the two. And let's see, pull the friction force to the other side. N sine of 6 degrees equals F cosine 6 degrees. And so N is equal, well, N sine of 6 degrees over cosine of 6 degrees equals F, the friction force. But what is sine of 6 degrees over cosine of 6 degrees? It's just tangent. So take the number you still have in your calculator and multiply it by the tangent of 6 degrees, and that's the magnitude of the friction force in the second case.
So 15.65 newtons.
6.5, so 7 or so. So there it is. There are the forces acting on the wedge in the second case. Now, are they really? Is it possible for the friction to generate that much force? Let's find out. Let's double check, because think about it. The most friction that can be generated is mu n. Well, mu n is 30% of the 148 newtons. What is 30% of 148? Roughly 50? Since the friction force is only 15 or so, 16, then sure, this friction coefficient can generate that much frictional force, so the wedge will stay in place. It won't just slip right out. What if we lowered the friction coefficient by putting some oil in between these two surfaces? Well, then it's possible that the friction coefficient would be lower. We wouldn't be able to generate enough friction force to hold the wedge in place, and it would just pop right out. How else could we get the wedge to pop out on its own? Well, we might change the angle of that wedge and increase the angle. If we increase the angle, notice what's going to happen. The normal force is going to increase its angle, which means we need even more friction force. And that's going to require more friction coefficient. Eventually, we'll overcome the friction coefficient. So another question could be, at what angle can this friction coefficient hold the wedge in place? Let's find out. That's actually a pretty easy question, because now the unknown is the angle. And if we want this sum to be 0, in other words, if we want the sum of forces in the vertical direction to be 0, the wedge to not come out, well, then that means the friction is going to be at its limit, mu n. See what happens then. So we already canceled the 2, so let me just write n sine theta minus, in fact, let me move it to the other side, f cosine theta. All right, let's see, is that what, yeah, that's what I want to do. Let's go ahead and rearrange it. It'll look like it did before. So, except I'll do this. Which way do I want to do that? I want to do it like this. Sine theta over cosine theta would be equal to the friction force over the normal force, but we're going to say that the friction force is at its maximum, mu n. So mu n over n, the normal force doesn't matter. It turns out that the tangent of the angle is just the friction coefficient. Okay? So if we take the inverse tangent of the friction coefficient, we'll get the maximum angle. And remember, this is the half angle of the wedge that we can accommodate. So go ahead and do that. Take the inverse tangent of 0.3. What do you get? 16.69? Okay.
Yeah.
Okay, so a little less than, a little less than 17 degrees would be the half angle of the wedge. Multiply that by 2. That's the total angle of the wedge that could be held in place in this ring. Would it take more or less force P to drive that wedge in if the wedge was a higher angle? It would take more force, right? Because then the normal force has a higher angle and is pushing harder and helping the friction prevent you from driving it in. This is why wedges are very narrow that you use to drive into wood. It's because the wood's actually held together very strongly. If you want to break it apart so you can fit it through the door of some type of burning device, you have to have a wedge that's fairly narrow. Any questions? Comments?